This is our second lecture in this lecture series, and the topic is operations on matrices with the following subtopics: 1. Addition of matrices. 2. Subtraction of matrices. 3. Multiplication of a matrix by a number. And 4. Multiplication of matrices. Addition and subtraction of matrices. Two matrices can only be added or subtracted if they are of the same dimension. That is, we can add the matrix A and B to obtain another matrix C if the dimension of A and dimension of B are equal, and the result C will be of the same dimension. So to obtain the element of C, we have Cij. That is the element of C in row I, column J, is equal to Aij plus Bij for each pair Ij. We can also subtract the two matrices A minus B to obtain another matrix C, where the element of C are Cij equals to Aij minus Bij for each pair Ij. Example 1. Consider these two matrices A and B. The dimension of A is 3 by 2. The dimension of B is also 3 by 2. So we can add the two matrices. A plus B is equal to this matrix plus this matrix. And to add the two matrices, we add the element in the corresponding positions. That is, we add 3 plus 4, 1 plus 6, 2 plus 1, 5 plus 2, 4 plus 3, and 7 plus 3. And this will give us 7, 7, 3, 7, 7, 10. Example 2. Again, let A be this 3 by 2 matrix, and this B be a 3 by 2 matrix also. Then we can subtract the two matrices. A minus B is equal to 3 minus 4, 1 minus 6, 2 minus 1, 5 minus 2, 4 minus 3, and 7 minus 3. And this will give us the matrix minus 1 minus 5, 1 3, 1 4. Multiplication of a matrix by a number. Let A be a matrix of any dimension and K be a number. Then the product Ka is obtained by multiplying every element in A by K. Example 3. Let A be this 2 by 3 matrix and K equals to 3. Then what is 3A? 3A is obtained by multiplying every element in A by 3. That is 5 times 3, 2 times 3, 4 times 3, 3 times 3, 0 times 3, and 1 times 3. And this will give us 15, 6, 12, 9, 0, 3. Multiplication of matrices. Let A be an M by N matrix and B be a P by Q matrix. Then the product AB is conformable for multiplication if n is equal to p. That is, if the number of columns in A, which is n, is equal to the number of rows in B, which is p. So before carrying out the multiplication of two matrices, we must first of all check whether the two matrices are conformable for multiplication. That is, we do this: AB equal to C. The dimension of A is given to be m by n. The dimension of B is given to be p by q. If AB is conformable for multiplication, then n must be equal to p. And the dimension of the product is m by q. Example 4. Let A be this 3 by 2 matrix and B be this 2 by 2 matrix. This is our A, which is 3 by 2. This is our B, which is 2 by 2. As you can see, this 2 is equal to the 2 here. So AB is conformable for multiplication. And that will give us a matrix C, and the dimension of C is this 3 by 2 matrix. Now, let us see how we can carry out the multiplication. Since the result C is a 3 by 2 matrix, let us write out the 3 by 2 matrix. AB equal to C equals to C11, C12, C21, C22, C31, C32. Let us now obtain the element of C. To obtain the element, for instance C11, we have to multiply row 1 of A by column 1 of B. This is how the multiplication is carried out. We multiply the row by the column. So C11 is obtained by multiplying this row 1 by column 1. That is 3 times 2 plus 1 times minus 4. That will give us 2. C12, we multiply row 1 by column 2. And that will give us 3 times 3 plus 1 times 5, which is equal to 14. C21 is obtained by multiplying row 2 by column 1. That is this row 2 by column 1. 2 times 2 plus 5 times minus 4. And that will give us minus 16. C22 is obtained by multiplying row 2 by column 2. Row 2 column 2. That is 2 times 3 plus 5 times 5. And that will give us 31. Next is C31. Multiply row 3 by column 1. Row 3 column 1. 4 times 2 plus 7 times minus 4. And that will give us minus 20. And finally, C32. Multiply row 3 by column 2. Row 3 column 2 will give us 4 times 3 plus 7 times 5. And that is 47. So therefore the product AB is equal to this matrix. Properties of operations on matrices. 1. Commutative property for addition. A plus B is equal to B plus A. 2. This is associative property for addition. A plus in bracket B plus C is equal to A plus B in bracket, then plus C. 3. A plus B transpose is equal to A transpose plus B transpose. 4. A minus B transpose is equal to A transpose minus B transpose. 5. Generally, the product AB is not equal to the product BA. 6. This is the associative property for multiplication of matrices. AB in bracket times C is equal to A times BC in bracket. 7. This is the reversal rule for transposition. The transpose of the product AB is equal to the transpose of B times the transpose of A. Observe the order is reversed on the right hand side. 8. The trace of A plus B is equal to trace of A plus trace of B. 9. Trace of A minus B is equal to trace of A minus trace of B. 10. Trace of the product AB is equal to trace of the product BA. Observe also here that the order is reversed. 11. Trace of ABC is equal to trace of CAB is equal to trace of BCA. Here we say that the trace of the product of three matrices is cyclically permuted. Example 5. Consider this 3 by 3 matrix A and another 3 by 3 matrix B. Let us verify that 1. AB transpose is equal to B transpose times A transpose. 2. That the product AB is not necessarily equal to the product BA. 3. That the trace of AB is equal to the trace of BA. Solution for number 1. Multiplying the matrix AB following the previous example, you multiply row 1 by column 1 to obtain 26, row 1 by column 2 to obtain 10, row 1 by column 3 to obtain 1. Then you use row 2. Row 2 column 1 will give you 17. Row 2 column 2 will give you 20. Row 2 column 3 will give you 14. Then you use row 3. Row 3 column 1 will give 16. Row 3 column 2 will give 11. And row 3 column 3 will give 12. Now the transpose of AB is this. Row 1 is now column 1, row 2 is now column 2, and row 3 is now column 3. Let us now find the product B transpose times A transpose. B transpose, row 1 of B is now column 1 of B transpose, row 2 of B is now column 2 of B transpose, and row 3 of B is now column 3 of B transpose. Then this is A transpose. This is row 1 of A becoming column 1 of A transpose, row 2 of A is column 2 of A transpose, and row 3 of A is column 3 of A transpose. Now multiplying these two, row 1, column 1 will give 26. Row 1, column 2 will give 17. Row 1, column 3 will give us 16. Now using row 2. Row 2, column 1 is 10. Row 2, column 2 is 20. Row 2, column 3 is 11. Then you use row 3. Row 3, column 1 will give us 1. Row 3, column 2 will give 14. And row 3, column 3 will give us 12. Now let us compare the two results. The transpose of AB is this. Then B transpose times A transpose is this. So comparing the two, you see that the two of them are equal. Solution of 2 and 3. The product AB, we recall, we obtain it to be equal to this in part 1. Now, the product BA is equal to this. Clearly, as you can see, these two matrices are not equal. So, AB is not equal to BA. The trace of AB is the sum of the leading diagonal element, 26 plus 20 plus 12. And that will give us 58. Also, the trace of BA is the sum of the leading diagonal element here. That is 15 plus 13 plus 30, which is also equal to 58. So you can see that the trace of AB is equal to the trace of BA. Theorem 1. Every square matrix A can be expressed uniquely as the sum of a symmetric matrix and a skew-symmetric matrix. Let us prove this. Let us express A as the sum of two matrices U plus V. And we number this as equation 1, where U is assumed to be symmetric and V is assumed to be skew-symmetric. Let us take the transpose of equation 1. Taking the transpose of equation 1, that will give us U transpose plus V transpose is equal to A transpose. But since U is a symmetric matrix, U transpose will give us U. And since V is a skew-symmetric matrix, V transpose will give us minus V. So this will give us U minus V is equal to A transpose. So let us number this as equation 2. We can now solve equation 1 and equation 2 simultaneously. In fact, we can eliminate V by adding equation 1 and 2. So this will give us U equal to half into A plus A transpose, and V equal to half into A minus A transpose. So clearly we can see that we can express the matrix A uniquely as the sum of U and V, where U is symmetric and V is skew-symmetric. Example 6. Let us express this 2 by 2 matrix A as the sum of skew. Let us express this matrix A as the sum of symmetric and skew-symmetric matrices. Solution. So we let A equals to U plus V, where U is symmetric and V is skew-symmetric. By our previous theorem, we had shown that U is equal to half into A plus A transpose. That is half into, this is the matrix A, plus this is the transpose of A. So adding these two matrices will give us half into 12 minus 2 minus 210. Multiplying half by this matrix will give us half times 12, 6. Half times minus 2 is minus 1. Half times minus 2 is minus 1. And half times 10 is 5. Clearly, this is a symmetric matrix. Next, we find V. V is equal to half into A minus A transpose. That is half into, this is our A minus this is the A transpose. Subtracting these two matrices will give us half into 0, 6 minus 6, 0. Then multiplying through by half, that will give us 0, 3 minus 3, 0. Clearly, this is a skew symmetric matrix. So we have been able to express A as the sum of symmetric matrix, which is this, plus skew symmetric matrix V, which is this.